Hi everybody, my name is Olivier Lefebvre and today I would like to talk about filter color and how we can look at that to understand when PM events are happening. I'm with Climate Solutions Consulting. Briefly what we do, we do assessments of clean cook stove intervention. We try to make them easier, more accessible, and to do that we've developed a suite of sensors that can be used to look at stove usage, fuel consumption, electricity consumption, and PM concentration. So why another sensor? Well, the stove usage and fuel electricity consumption is working really well right now, but PM 2.5 measurements remain pretty hard to do because we don't have yet good instruments to do those measurements. There is light scattering based sensors. Those are small, but they have major limitations because their sensitivity is dependent on the aerosol size distribution and absorption properties. They also need to be able to measure very large dynamic range, and it's hard to have a sensor that's both good at low concentration and high concentration. And they have a fairly big power requirement at lower concentration. On the other hand, gravimetric samplers are more accurate, but they are bulky and difficult to work with. And also they only provide an average over the sampling period. So of course you can use those two sensor types together, but then it's even bulkier, and that creates some issues with compliance and bias. You know, when you ask people to wear those sensors, that will create some difficulties. So there's no good easy solution yet for this. So that's why we've been thinking of what we can do. And we think that it's important to stick with gravimetric sampling because it's really the only accurate method. But can we look at the color of the filters to give us an indication of when those PM events are happening? Because it's important to know where they're happening and where they're coming from. So that's what we're going to try to explore today. But first, I would like to talk a little bit about the different method to look at that. You can look at the transmittance of the light through the filter or the reflectance of the light by the filter. The difference between those two methods is where you put the light source. For transmittance, you'll put the light source across from the sensor, whereas for the reflectance, you'll put the light source at the same side as the sensor, and you look at the light reflected by the filter. There is already several instruments that exist that using those methods. It's not a new concept. The main one is the one developed by Maggie Scientific, the affalometers to look at black carbon. They also develop portable ones with the company AFLabs, but there's also new sensor coming up, especially the one from Distributed Sensing Technologies Observer, that address some of the limitation of those previous sensors, specifically the dependence on the influence of relative humidity. But here what we propose is to use those two methods together by doing transmittance offline before and after on the filter, and doing reflectance inline and logging every minute the reflectance of the filter. To do that, we come up with a suite of sensors that look a little bit like that. So this one is the reflectance sensor. There's a very similar one for transmittance. Here we have both the sensor and the light source on the same side of the filter. You see they're very small. They've been made to fit a standard 30mm cassette. And you see there's the O-ring here that ensure good still with a standard cassette. And on the left picture, you can see the different LEDs and the light sensor. The light sensor we're using is a SI1153 from Silicon Labs. These combine both a light sensor and a LED driver, and that can drive up to 3 LEDs. So we put a UV LED, infrared LED, and a red LED. We also added a temperature and relative humidity sensor because we know that those environmental parameters have an influence on the measurements. So first question is, can we, what's the correlation between those two ways of looking at filter change, the transmittance and the reflectance? And so this is a scatter plot of those two methods for the sensors we developed. And you see there's a fairly good correlation. There's still a little bit of error that's introduced between those different methods. It's really a first iteration here, and we hope that we'll be able to improve on this and make it a little bit better. The second question is, what's the transmittance between, what's the correlation between, on one hand, our sensor, the transmittance sensor, and the transmittance sensor from Maggie's scientific DOT 21 scan. Here you see there's fairly good correlation between the two. There's still a little bit of offset left, and so we hope we can improve on that and make it a little bit better. The next one is the inference of temperature. We know temperature is a source of impact on the sensor since LEDs depend on temperature. So here we have those two measurements. The inference is linear, and so when we correct for it, you have here the residual error that's left. Thankfully, the residual is fairly small. It's less than 0.15% of the readings, and so we've mostly corrected for that. But what about real-time PM detection? To look at that, we've come up with very simple protocol. We've placed in a closed smoke chamber. We placed Apex sensor and the new sensor that we've developed. We put a fan to mix the chamber and a source of PM here, incense sticks for convenience. And we looked at the two signals from the Apex, the light scattering device, and from the filter cassette. And so here is what we got. In red you have the Apex, in green you have the slope of the reflectance. And you see that the event was detected, although the slope decreased a lot faster than the actual concentration here. It was a fairly big concentration. Here you have the measurements in microgram per cubic meter. We did calibrate these using gravimetric measurements. So fairly high concentration, but also short duration of the event. And so we think that for longer events, we'll still be able to detect those. Of course, there is quite a bit of work left to do. The next step would be really to characterize the PM limit of detection accuracy with actual cook stove emissions, but also to look at the potential of using the data from the different channel, the infrared, the red, the ultraviolet channel, to do some source apportionment and being able to differentiate emissions from a kerosene lamp and a freestone fire, and maybe emission from dust, from laterite dust or something like that. So we hope to be able to do that and at least explore whether or not it's possible. And also would like to characterize the influence of relative humidity a bit better on this sensor, because we know it can have an influence. So if that sounds interesting to you and you would like to contribute and help with that, you're more than welcome to reach out. We'd love to work with other groups to try to make those sensors most useful and good tool for the sector. So feel free to reach out. Thank you so much for your attention. I'm looking forward to hearing your thoughts on this. Bye.